So I picked out two more sets of problems to look at from this monster list of problems, and I decided that since after section C, they're basically in bundles, rather than just do like one, I would just do the section, and we would kind of treat this as somewhere in between I do a problem and I continue kind of giving the lecture part of the class in order to show more applications of these ideas. So in 16D, what we do is we're studying the group of inner automorphisms of a group. And so this video will be longer than other ones that we've done. And I'm going to work through this kind of one piece at a time. So in the first part, we fix a group G, and we remember that aught G denotes the functions G to itself, where phi is an isomorphism, right? The self isomorphisms of phi, if you will, or of G, sorry, I should say, not of phi. And so the first step is to prove that aught G is a subgroup of SG, the permutation group on the set G. And let's see. In order to do that, I need to see that it's a subgroup. And of course, I should probably say the operation is composition. So to see that it's a subgroup, what that means is I have to see that every element of aught G is a permutation of G. Well, a permutation means a self-bijection. And an isomorphism is a bijective homomorphism. And so there it is, right? This is a self-bijection. Great, we did that part. We unraveled the definitions to see that that's true. The next step is he defines an inner automorphism. To be, I should say, is an automorphism of the form. Let me just use his notation. Phi A of X equals AXA inverse. Okay, and then the question is to prove inner automorphisms deserve their name. They're actually automorphisms. So I need to prove it's a homomorphism and it's bijective. Okay, so first let's do homomorphism. I have to prove phi A of xy equals phi A x phi A y. This guy is AXY A inverse, and this is AX A inverse, AY A inverse, or AX A inverse AY A inverse. And would you look at that? These guys cancel, and it's a homomorphism. Now, why is it bijective? We need to show it's injective. So I assume that phi A of x equals phi A of y. And I get this equation. But of course, right, multiplying on the left, multiplying on the right implies x equals y. So it's injective. And now I need to prove it's surjective. So in other words, I need to prove that every y in G is phi A of x for some x. Well, if I have a y, let's see, what's the simplest way to say why this is? I want to solve y equals AXA inverse. So now I write A inverse x, or sorry, y, A equals x, multiplying on the left and right. This is equal to a, what am I trying to say here? If I set alpha equals A inverse, then this is alpha y alpha inverse because A inverse inverse equals A. So therefore alpha inverse equals A, which is that would be it's a phi alpha. It's not really what I mean to say. So what do I mean to say? This isn't doing what I want to do. Um, okay, but I do see what I do want to do. Sorry, this doesn't work the way I've written it. We kind of fell into a little bit of a trap, but it's okay. I know how to fix it. What I want to do is instead say, like, I want to know what's the x that does this. And I actually had it. X equals A inverse y a equals x. And so if I take this x and then I apply phi a, then the a and the a inverse on either side will cancel. So I actually kind of overthought it. Phi a of x is y. Okay, we checked it. We got surjective. Okay, let's keep going. Part 3 says prove that for arbitrary a, b, and g, phi a composed with phi b equals phi ab. And also, phi of A inverse equals phi of A inverse. All right, that seems very straightforward. The easiest way to do this is to check it on an element. So phi A of phi B of x equals phi B of x, which is phi A of bx B inverse, which is ABX B inverse A inverse. And now I need to get that that's also the same thing as phi AB. So let's calculate that. That is ABX, AB inverse. And these two things are equal by shoes and socks. Right. AB inverse equals B inverse A inverse. All right, that handles this part. Phi of A inverse. Well, let's check it again on an X. This is A inverse inverse X, A inverse, which is AX, A inverse. Phi of AX, I'm realizing, did I copy this down correctly? Oh yeah, it's right. Because phi of A inverse the map, it doesn't mean phi of A inverse of X inverse. This is the inverse map. In other words, what is the function that undoes this? Um, and the easiest way to see that this is the inverse of this is to just calculate it. In other words, to just plug this into that. So the inverse permutation, well, I'm not sure how to say this. In light of what we said about surjectivity, right up here, we calculated that if I plug this in to phi a, I get back the desired y. Well, this is the same form, right, with the inverse on the right. And so if I plug this in to phi of a, then you get A inverse A x A inverse A. Wait, hold on. I think my inverses got switched somewhere. Yeah, they did. Um, where did I start making this mistake? It's right here. This is okay. Oh, I see. The issue is here. I have too many inverses. They're backwards here. This should be A inverse, and this is the one that gets inverse inverse. Okay, hold on. Sorry about this, friends. Very unprofessional of me. This is A inverse X, A inverse inverse. And this is the one. Yeah, and now what I was saying isn't true here, but it's right now. Now, when I apply phi A to this, then I get A inverse, X, A inverse, which is, of course, just X. And that shows that phi of A inverse is the inverse permutation to phi A, which is what I wanted to show. All right, sorry about the confusion. I've got to double check that. Okay. So now we have part 4, which says we use the notation I of G to denote the inner automorphisms. What are we asked to prove? We're asked to prove using part 3 that I of G is a subgroup of ought G. And in particular, explain why I of G is a group. Okay, so why it's a subgroup of ought G is close to done already, in the sense of it's clearly a subset. Basically, all I have to do is explain why it's a group, and then we'll be done. And so the reason is because of what we just said, right? Namely, that under the operation of composition, these things compose according to these rules. Phi of A composed with phi of B is phi AB. And so, in other words, conjugation respects composition. And similarly, conjugation by the inverse is the same thing as the inverse composition. And so, under the operation of composition, we're done. This is basically, they said use part 3, but the answer basically is part 3. So we're happy. Now, part 5 says the center of G is the set of all elements that commute with everything. We have a definition. He writes C equals those A and G such that AX equals XA for every X in G. And then he says, prove that A is in the center if and only if AX A inverse equals X. And this is trivial because if I just multiply both sides of this equation by A on the right, I get that equation. And so this is also supposed to be for every X in G, but I think you guys know that. And so this is just the definition. You're in the center when conjugation fixes you. All right, we're almost done. Part 6, we have a function h, not from C, from G to I of G, which takes h of A equals phi A, essentially. That's what he writes. Prove that H is a homomorphism. And C is its kernel. And again, these are basically the definitions. What does it mean to be a homomorphism? It means that H of AB equals H of A, H of B. H of AB is phi AB. This is phi A composed with phi B. This was part 3. And then the kernel is the H of A such that this is the identity element in I of G. Well, this is the elements of I of G are the things that, as a subgroup of ought G, subgroup of ought G. So therefore, we're asking for the identity permutation right? The identity function. And so the question is, which h of a's are equal to the identity as a constant, or sorry, the identity element of ig is the identity permutation. In other words, h of a is just equal to a. Well, if h of a is equal to phi of a, phi a of x is ax a inverse, and I want this to be equal to x so that it can be the identity function. That is what we just said in the previous bit. The kernel is equal to the collection where the collection of a's where axa inverse equals x, and we just said that that is exactly the center as defined. And now the last part is to conclude that I of G, the inner automorphisms, are isomorphic with G mod C. Well, the fundamental homomorphism theorem says I have a function G to I of G, right? That is H. The projection to G mod C is the natural map, and the kernel of H is equal to C by our calculation. Sorry, this should be a solid line. So here is the isomorphism that's claimed by the fundamental homomorphism theorem. Okay, like I said, this has been I've been talking a little bit longer than usual, about 15 minutes now. I want to make kind of one more remark that's not in the problem, but it feels like it's generally important. This is that when you are studying a group, studying automorphisms is a pretty reasonable thing to do because it sort of tells you how canonical your calculation is. In other words, like you could ask, is there some automorphism of the group, some self-isomorphism, some other way of writing the group that might be easier to work with? Right? You want to know these because they can help you choose reasonable ways of doing calculations. But what we're seeing here is that the inner automorphisms are kind of actually they're not unimportant by any stretch of the imagination. But in terms of like writing things in different ways, we have seen this trick of like inserting the identity a bunch of times, right? Where did I first use this trick? Here, right? Where the identity is inserted and then it cancels. And that's not really like a non-trivial way of rewriting an equation, right? It's a sort of silly insertion. So oftentimes what we're interested in are actually the non-inner automorphisms. And so if we're interested in the non-inner automorphisms, then we know that since the inner automorphisms are basically, because of this fact, the inner automorphisms are isomorphic to G mod C, we might be interested in what you could call the outer isomorphisms, which are what you get when you mod out by the inner automorphisms. And so this is very easy to find. And therefore, if you know something about this group, you might then be able to look for interesting outer isomorphisms that can help you. And so one of the things that you're asked to, or not like, you're not, this isn't one of the mandatory problems, but one of the things that you can look at in the homework is what are the automorphisms of the symmetric groups themselves? And in particular, there is one instance of an exceptional outer automorphism in particular, where this is something that might be like, it can be good to know about. And I would call this a good application of the theory of automorphisms for understanding symmetric groups. Okay, I got one more of these prepped, sort of sections of problems. And so I'm going to leave this here and let you guys take a look at that.